Hopefully everybody had a good break. Ready to kind of get back at it. So one thing I wanted to mention off the top is I believe, and I'll double check that it's the same for your section. But I think I have this Connect assignment due date to be Wednesday. I meant for it to be Friday, so it's due at the end of this week. Should be able to get through all of it, even of it, but everything's from before spring break. We've got the Excel assignment, which is kind of last questions of the stuff that we covered this week. In fact, we'll probably go over the Excel portion of what we talked about today on Wednesday. Okay. And that's not due until the end of next week. Okay. So it's kind of where we stand at with that. Other than that, are there any questions for me before we kind of jump into it here today? Yeah. So we left off as a little bit of a review, thinking about, we've got these sample means, and we said they're normally distributed, as long as we have a sample size over 30, around whatever the true population mean is. We also said that the variance of our sample means was whatever the original variance was over our sample size. Okay. So we're going to use this kind of some of the stuff that we talked about today, what we know about that kind of distribution of our sample means. Okay. So what we're going to want to do is typically, I was kind of going through this thought experiment, like where I had population data and I just kept taking samples and then I could see how they're distributed. In practice, we usually only have one sample. I usually only see one sample mean. Maybe it's over here, maybe it's over here. So what I want to try to do is guarantee that the sample mean I'm seeing is as informative about what the true population mean is as possible. Well, how can I do that? We said we want to make sure that they're unbiased, right? We want to make sure we have these kind of unbiased samples. We talked about selection bias, all these other things. And then we also want to make sure that whatever the distribution of our sample means is, we want to try to get to be as small as possible. Because if I can get the variance to be smaller, what happens to this distribution? We said it becomes more peaked, and that the values around the true mean are going to be more likely for us to see from our sample mean. So I want to try to get this low variance, which means one thing I can do that influences that, take a higher sample size, right? Taking a higher sample size makes this variance smaller, gives me this more peaked distribution. Okay. So what we're going to do is then use that sample mean. We only see one sample mean. But we know that it's probably very unlikely that, we get, in fact, what's the probability that our sample mean is exactly equal to the population mean? Or what's the probability that it's exactly equal to one value? We said the probability of any one specific value is actually 0. So we're almost guaranteed that I'm going to see a sample mean that varies a little bit from whatever that true population mean is. So what I'm going to do is say, okay, look, I know that I'm unlikely to see this exact value. I'm probably going to see something over here, over here, over here. So what I'm going to do is whatever sample mean value I find, I'm going to build a confidence interval around it, what I'm calling it, but I'm going to kind of go a certain amount to the left, a certain amount to the right, get an upper and lower bound, and then say, okay, look, this is the sample mean I found. I know that's probably pretty close to the population mean. So if I go out a certain amount to the left and the right, there's a pretty good chance that the true mean is somewhere in this range. If I saw a sample mean over here, and I built a confidence interval. Okay, now that confidence interval includes the true population mean. Okay. So what I'm going to do, skip ahead here. There we go. What I'm going to do is I'm going to take whatever sample mean I find and add and subtract a certain amount to it to get this upper and lower bound, where I can then say with 90% confidence, the true population mean is somewhere in this range of values. And this range of values is going to be based off of whatever I saw from my sample. So if we go back here, right, just to kind of get some definitional stuff. So let's say we're trying to, we've got birth weight, and we want, we take a sample, we see a specific value. Well, we know it's probably going to be a little bit off, right? So we want to build this confidence interval around that value. And when we say confidence, we'll get a little bit more precise about this here in a second. But I can say things with different levels of confidence. So I can say things with 90% confidence, it's in this range. With 99% confidence, it's in this range of values. Okay? But all of these confidence intervals are based off of, or they're centered around, whatever sample mean value we found from our data. So whatever our sample mean is, we're going to build a confidence interval around that, and we can build different levels of confidence. I can build a 90% confidence interval. I can build a 99% confidence interval. So how do we choose this W, right? I'm telling you we go a certain amount to the left and to the right, so you can kind of think about it here. I'm going the same amount to the left and the right to get my upper and lower bound. So what is that confidence interval going to be? So skip ahead here. Let's say, I'm going to put this up here, and then I'm going to kind of draw this out. Give you hopefully a slightly better idea of what we're doing here. So let's say I've got the distribution of my sample means, and I want to build, I see some sample mean, I want to build a 95% confidence. We're going to use something we know about normal distributions, which is my black marker. That if I were to go a certain amount of standard deviations to the left and to the right, there is a certain number of standard deviations I could go that would give me 0.95 in the middle. How can I find that? Well, I can actually use the inverse process that we've already talked about. Because I know that if I'm looking at the standard normal distribution, and I want 0.95 in the middle there, what's going to be the total area outside of that range? So there's going to be 0.025 in each tail, right? The total area outside of this range would be 0.05. So I'm going to have 0.05 in each tail, or 0.025, sorry, 0.05 total in the tails, 0.025 in each tail. Well, this is great because now, if I know the area in the tail, I can use the inverse process to figure out how many standard deviations away do I need to go to get 0.025 in the tail. Or, said differently, what's that Z value? So we'll go to our table. We know we want that area of 0.025. The corresponding Z value is 1.96, right? So I need to go 1.96 standard deviations above and below to get that area of 0.025 in each tail, or to get that 95% confidence in the middle, right? So I know that whatever sample mean, or sorry, if I go back up here to my sample mean distribution, if I were to go 1.96 standard deviations above and 1.96 standard deviations below, right? The area in the middle there, the probability that I'm within 1.96 standard deviations above and below that true population mean, there's a 95% chance, right? So this range of values that I want, right? I want to be able to say with 95% confidence, or there's a 95% chance the true population mean is somewhere in this range of values. So now that we know the number of standard deviations away we need to go, and kind of address something else. So before we do that, are there any questions over this idea? So all we've done up to this point is kind of use that inverse process to figure out how many standard deviations away do we need to go to get that desired area in our tails, right? Alpha over 2 in each tail. Any questions on that before we keep moving? So I think this might help make some sense of what we're going to do next. So before we go to the slides, let's say, let's say I see a sample mean a little bit below that true population mean. If I go 1.96 standard deviations above and below that, what I know for this sample mean, notice it is less than 1.96 standard deviations below, right? Maybe it's like 1 standard deviation below. Okay, then if I add 1.96 standard deviations to it, I'm going to end up with an upper bound that's on the other side of that true population mean. Right? And if I see, you know, a sample mean that's out here, and I go 1.96 standard deviations below, 1.96 standard deviations above that sample mean value. Well, this sample mean was less than 1.96 standard deviations away. So when I subtract 1.96 standard deviations from it, my lower bound will be a little bit That's that true population mean. So any sample mean that's within this range of values, if I add and subtract 1.96 standard deviations to those sample mean values, I'll always get a confidence interval that includes the true population mean. So with 95% confidence, if I'm adding 1.96 standard deviations above and below whatever sample mean value I see, 95% of the time, I'm going to end up with a confidence interval that includes that true population mean. The problem is, if I see a sample mean way out here, well, now if I go 1.96 standard deviations above and below, for sample mean values that are way out here, this was like more than 1 point, it's like 2.5 standard deviations maybe away. So now when I subtract 1.9, I'm going to end up with a value that's still slightly above whatever the true population mean is. So for every sample mean value in this range, I'm going to end up with a confidence interval that's actually wrong, right? I'm going to end up with a confidence interval that actually doesn't include the true population mean, which is why when we build these confidence intervals around just one sample, we're saying, look, I've got this confidence interval. I built it around the sample evidence I found. There's a 95% chance the sample evidence I found is within this range. There's a 5% chance it's outside of here. So there's a 95% chance that my confidence interval is correct and includes that true population mean value. There's a 5% chance that I'm wrong, right? But we can, it's the best we can do, right? Based off of only having one sample. So I think here I kind of have a similar visual in the slides. I just thought maybe having the 1.6 kind of thinking about it's going to help a little bit before we get to it. But the idea is, right, any sample mean in this range here, when I add 1.96 standard deviations above and below it, I've got a confidence interval that includes true population mean. But as soon as I get a sample mean that's kind of outside of that range, right, my confidence interval won't include that true population. Any questions on that idea before we keep moving, or clarification on anything? We'll get to some actual problems here in a second. Get all this up here and then we'll kind of keep moving. So one thing kind of terminology wise that we'll start doing, we have these different levels of confidence. They're always going to have a corresponding what we call alpha, right? So I had it written up here before. Everybody can erase this. Anybody still need anything up here? Okay. So before, I used one specific example, which was the 95% confidence interval. But I can do 99, 95, 90%. I can do whatever confidence level I want. We generally use these three because, like, just kind of nice benchmark values, 90, 99, 95%. But what we were doing initially is that we looked up, we wanted 0.95 in the middle, but it doesn't matter what area we want in the middle. What area is always going to be kind of outside of that range? Well, if I've got a 95% confidence interval, that means there's 5% outside of it. If I've got a 90% confidence interval, there's 10% outside of it. If I had an 80% confidence interval, 20% outside of it, right? So I always know that the area that's going to be outside my interval is going to be the area that's in my tails here. Problem is, we're not talking about percentages, we're talking about probability, right? So instead of 10% outside the interval, that would be a probability of being outside the interval of 0.1. So we're going to call kind of alpha the total area that's outside of my interval in decimal form. That's like not the most textbook definition of it, but it's an easy way to remember it, right? However, I know alpha is the total area in my tails. So the area in each tail is actually going to be half of alpha. Right? Well, now once I have this area I want in the tail, I can find that corresponding z value. So we're always going to be looking up the z value that corresponds to having alpha over 2 in our tail. And once again, alpha is just the total area outside of our interval in decimal form, so it's probability. And then we divide it by 2 because we've got a side, we've got two sides of our confidence interval. We got an area above it, we got an area below it. So, we can work in either direction, right? If I tell you it's the 99% confidence interval, well, what area is outside of it? 1%, decimal form, alpha is 0.01. If I tell you that alpha is 0.2, okay, well, that means that there's 20% outside my interval. That means the area in my interval would be 80%, right? I can work in either direction. But once I know that I want alpha over 2 in the tail, that's the, I want to find how many standard deviations away do I need to go to get that desired area in the tail. And then I'm going to take my sample mean. To get my upper bound, I'm going to add whatever number of standard deviations that was. And if that's the number of standard deviations away I need to go, I then need to multiply that by, well, what's the standard deviation of the statistic I'm looking at, right? I then subtract that same thing to get my lower bound, right? So we think about our confidence interval equation, it's going to look something like this, right? I'm going to take that sample evidence, that sample mean I found, I'm going to add, and what I'll kind of call this on the right, we'll call this our margin of error. I think technically you're not supposed to do that unless we're dealing with proportions, which that stuff we'll do Wednesday. But it's a nice easy term that I can assign to what we're adding and subtracting here. This is our margin of error, right? I add that margin of error to my upper bound, I subtract that same amount to my lower bound. Now I've got whatever confidence interval I have, right? 90, 95, 99%. I can build all kinds of confidence. And we'll see how we do this in Excel pretty quickly on Wednesday. Any questions on this before we keep moving? So what's another way I can write this based off of some things that we've already talked about? So remember, when we were thinking about the variance of our sample means, it was just the original variance of the data we sampled from over our sample size. So if we want the standard deviation, we could kind of plug that formula in here and do this all at once. I think some of the examples I'll show you that we'll work through today, I always break this down into parts. It's just easier to kind of think about, like I figure out what that standard deviation is in my sample means first. That way I only have one value to plug in. But if you wanted to, you could write this out, and plug that formula in, and do this all in one line. Right? So we'll see what this looks like with a couple, or with an example, and I'll come back to that slide to kind of talk about some things. So we've got our confidence interval equation. Let's put some actual numbers to it. So it might seem like a stupid example. I'll try to give you why it matters more after we're done with the example. But for now, I'll just go with it, right? So let's say we've got some production process and we're creating coffee cups, right? And they're supposed to weigh 7.5 grams. Okay. So, or sorry, they're supposed to weigh, let's say, 9 grams. We take a sample and we see that from our sample of 49, we only have a weight on average of 7.5. Right? So we're kind of off of our target, right? But it's just a sample, right? The true population mean could be that targeted weight of 9 grams. So what I'm going to do is I'm going to take that sample mean, build a confidence interval around it, and hope that that targeted value of 9 is one of the values in my range, right? So we'll identify the things that we are kind of told. So we found the sample mean of 7.5. I sampled 49 of these hockey pucks, right? I can't sample every single unit that I produce, but I grabbed 49 of them off of the assembly line. Now this is where it gets a little bit hokey. I'll kind of explain it away in a second. But let's assume someone told us that the population variance of the production process is 49 as well. Somehow we know that, right? And I want a 99% confidence interval. So my alpha value would be what? 99%. Yeah, 1% outside. In decimal form is 0.01. Okay. So I've got kind of all the pieces of information that I needed that I was given to kind of start plugging in here, right? I've got 7.5 was my sample mean. Both of these were 49. That kind of made the math a little bit easier. The only thing left I need to do is figure out, well, what's that Z value? What's the number of standard deviations away I need to go to get alpha total outside of my interval? Well, if I want alpha total outside of my interval, how much would be on each side? Half of alpha, or 0.01 over 2, 0.005. Okay. So remember, it's always going to be, I need to find the Z value that corresponds to having half of alpha in that tail, right? Well, now that I know the area I want in the tail, I'm just using my inverse process. Go to my Z table, hunt down 0.005. Looks like I'm in between these two values. So well, did I look at this right? 2.5, negative 2.57, negative 2.58. So the number of standard deviations above and below I need to go will be 2.58. Now, when I look up alpha over 2, I'm always going to be looking at the left side of my distribution. So I'm always going to find the negative value. But notice that's already built into my confidence interval equation, right? I'm subtracting 2.58 standard deviations to get my lower bound. I would then add that same number of standard deviations to get my upper bound. Okay? So we'll always find the negative value, but the sign's already built into our equations, right? Subtract that number of standard deviations to get our lower bound, add that same number to get our upper bound. Questions on that? Oh, is there anything else I wanted to say about this? We'll go back to the slides. I've got something else I want to say. Okay. So we identified, here's kind of a slide I put in. This is the general form of what we're going to do. We'll identify the 4 things that we need: sample size, sample mean, the original variance, and alpha. We'll then look up that z value that gives us alpha over 2 in each tail. You could have calculated the standard deviation of your sample means as an intermediate step, as opposed to like plugging it in all at once. I generally think this is actually probably a good thing to do, or makes it a little bit easier. So that way I only have one value to plug in here. Right? So you can do it like I have up here on the board, where we plug everything in all at once, or you can kind of do the intermediate step. If we do that, this one, it was kind of nice and easy. The standard deviation ended up being 1. Well, now I've got everything I need, right? I've got this whole guy here, just simplified down to 1. Now it's just a matter of plugging those in my confidence interval equation, add that margin of error to get my upper bound, subtract it to get my lower bound. So based around this sample mean, with 99% confidence, I can say the true weight of my production process of these hockey pucks is somewhere between about 5 and 10 grams. Right? Now that's a pretty wide range. Like if I'm targeting 9, I'm happy with this, right? Because 9 is one of the values in that range. But if I'm targeting a weight of 15, I have a problem, right? My production process is not hitting what I want. Right? Now this seems like a really dumb example with hockey pucks, but you can imagine, like, if this was the weight of some substance that's in medication, it becomes a lot more important, right? I need to really make sure my production process is, putting whatever level of this medication in these pill capsules, right? I can't sample every single pill, right? I can only sample a subset of them, right? So we want to kind of get as narrow of a range as possible, right? I really want to make sure with 99% confidence I could tell you that the true weight is in between, like, I don't know, 7.11 and 7.13, right? Really, really narrow range. So how can I do that? Well, I don't really have any influence over what the original variance is of the data I'm sampling from. It just is what it is. If I want to say things with higher levels of confidence, what's going to happen to that z value? So let's say I want to say something with a higher level of confidence. What's going to happen to alpha? So I go from 90 to, or sorry, we were at 99. 99 to 99.9%. Right? What's going to happen to alpha there? It's going to get smaller. So alpha over 2 is going to be a smaller value. So if alpha over 2 is a smaller value, what's going to have to be true about the number of standard deviations away I need to go? I'm going to have to go a higher number of standard deviations away, right? This might be something like, I don't know, 3.5 or something like that. Okay? So when I want to say things with higher levels of confidence, I'm going to have to go a higher number of standard deviations away. So what's going to happen to my confidence interval? Well, I'm now adding and subtracting a larger margin of error. I'm getting a wider range of values. I think it's kind of intuitive. If I want to say something, with 90% confidence, the true average income in the US is between 50 to 60,000. Well, if I want to say with 99% confidence what it's in between, I'm going to have to give you a wider range of values, right? So, and that kind of just comes from, if I want to say things with a higher level of confidence, I'm going to have to add a higher number of add and subtract a higher number of standard deviations to get my upper and lower bound. So we want to say things with higher levels of confidence, which is going to be a smaller alpha. I'm going to get a wider interval, right? Well, that's kind of a problem, right? I want to be able to say things with a very high level of confidence, but the wider my range of values get, the less useful it is, right? If I tell you that, yeah, with 99.999%, the average income is in between 20 and 100,000. Oh, okay. Well, I mean, I probably could have told you that without actually looking at any data, right? So I want to try to make sure I can say something with a high level of confidence, but get a really narrow range of values. So what's the thing that we can influence that even if we wanted to say something with 99.99%, I could still get a really narrow range of values? If I jack up my sample size, right, make sure I'm taking a really large sample, what's going to happen to that standard deviation of my sample means? Right, the denominator gets larger, it's going to get smaller. I'm then adding and subtracting a smaller amount to that sample mean, I'm getting a much more narrow range of values. So when I take these really large samples, I can use a really high level of confidence, but still get a pretty narrow range of values because my sample size was so large. Right? And that's going back here. Skip that slide, but we'll talk a little bit more about this here in a second. There we go. So I kind of already addressed two of these, right? One, we take a larger sample size, we're going to get this kind of smaller, narrower range of an interval. Right? If I want to say something with less confidence, that would actually be a larger alpha value. Well, if I want to say something with less confidence, I don't have to give you as wide of a range. So it's the exact opposite of how I described it, right? You can kind of go in either direction, right? If I want to say something with a higher level of confidence, that's a smaller alpha. That's going to be a higher number of standard deviations. It's going to be a wider interval. If I want to say something with less confidence or a larger alpha value, right? 99 to 90%, alpha goes from 0.01 to 0.1. Right? Well, then with that larger alpha or lower level of confidence, I don't need to go quite as many standard deviations away. So if my z value is smaller, I'm adding and subtracting a smaller amount. For these lower levels of confidence, I'm getting a narrower range. And then the one that I didn't talk about, because we don't really have any control over it, is, well, what's the original population variance? Because if the original population variance goes up, well, then my margin of error is going to go up. I'm going to get a wider interval, right? And that kind of intuitively makes sense as well. If the original data is just more varied, well, it's going to be less likely our sample mean is as informative. So we're going to need to have a wider interval to kind of guarantee the true population mean is included. Now, one thing that's kind of hokey about this, and I always am like surprised that I guess maybe people are not, I don't know. I'm most surprised someone doesn't ask this yet up to this point. But the whole purpose of what we're doing with confidence intervals is we don't know the population mean. All we have is our sample mean. It's our best guess, right? So how the hell do we know the population variance if we don't know the population mean? And the answer is we've got to walk before we can run. If we, in practice, we usually don't have a population mean. All we can observe is a population variance. All we can observe is a sample variance. But that kind of screws some things up for us and makes it a little bit harder. So I'm first starting out with these examples where somehow just assume that somebody told you the population variance, right? We're going to still use that Z table, kind of get those problems down. Once we're kind of more comfortable with those, we'll kind of go to the next step, which is, well, we probably don't have the population variance. If we don't have the population variance, what do we do then? Right? So that's coming in the future. But for now, just assume somehow you know the population variance. And it's not the wildest assumption. Like, I don't want it to be like there's no application for this. So you can imagine like in the hockey puck thing, if I'm pouring these hockey pucks into a mold, I might, based off of engineering, physics, all this stuff, know the variance on my machinery, right? I might know what the variation is on this, whatever the pouring process is to make these hockey pucks. I just may not, know if it's calibrated to be the correct average, right? So there are instances where we will know the population variance on our production process, but we just can't sample every single product, right? But I would be lying if I said this is the most common application. Usually we won't have the population variance, and we'll kind of deal with that later on in this week. Okay. All right. So we went through one example. Let's go through another one. So let's go back thinking about some of that birth data we were looking at. So let's say I've got the length of a pregnancy or the gestation weeks, and I'm trying to kind of narrow down on average how long does a pregnancy last, right? So I take a sample, I got a sample of 81 births, so my sample size is 81, and I find that on average over those 81 births, the average number of weeks was 38. Okay? I then somehow know the population variance. Once again, it's going to be a little bit hokey until we've got to walk before we can run, but somehow we know the population variance. Someone tells us this. Okay. If I wanted a 95% confidence interval, what's my alpha value going to be? Remember, alpha is just the area outside my interval in decimal form. So 5% outside, yep, 0.05, right, is the decimal form of that. Okay. So if I think about the formula that I have for my confidence interval, and we could do it in two ways, right? I could first calculate the standard deviation of my sample means and then plug one value in, or I can do it all at once. I'll do it where I break it down here. But I've got my sample mean. I can find that standard deviation by taking the original population variance of 9 divided by that sample size of 81. I think this works out to be what? 1/3. Right? The only thing left I need to do is figure out, well, how many standard deviations away do I need to go? In fact, if we've been paying attention, you might already know what that value is supposed to be. If I want a 95% confidence interval, that means the total area outside that interval is going to be 0.05. Well, if I've got two equally sized intervals, that means I've got half of alpha on each side, or 0.025. But in the example we did earlier, we already looked that up in our Z table before. Anytime I have a 95% confidence interval, the area in each tail is always going to be half of alpha. So 0.05 over 2, it's always going to be 0.025. When I look 0.025 up on the table, I'm always going to find that same corresponding Z score of 1.96. So I know that the Z value, or the number of standard deviations where I need to go, is 1.96. All right. I'll then add that margin of error to my upper bound. I'll subtract it to get my lower bound. And then I can say, with 95% confidence, the true length of pregnancy is somewhere in this range. Okay. So I think I've got kind of that outlined, maybe not as detailed here. All right. Once we had everything that we needed, I'm just going to plug everything in. Now, once again, I would just find the intermediate step first. You could have kind of, written it all out in one line. I wrote it up here a little bit differently. Remember, in this case, it doesn't really apply, but I did this so I'd remember to mention this. Here, I had the variance, so it's probably easier to calculate it this way. We said mathematically, another way you can write that, if I'm taking the square root of something that's squared, it's just itself. So if I instead had the population standard deviation, it might be a little bit more useful to use this form of the equation, but they're really the same thing, right? It's just one of them is simplified a little bit. Okay? And like I said, if I'm doing this by hand, I'd probably calculate that intermediate step, just makes it a little bit easier. Any questions on this before we keep moving here? So I've got a pretty narrow range here, right? With 95% confidence, I can say that the true length of a pregnancy on average is between what, 37.3 and 38.6 weeks. Okay. So a couple of things about my confidence. It should always be centered around my sample mean. So my sample mean should always be smack dab in the middle of it, right? So if I'm thinking about, if I gave you some options and I said, which of these is the confidence interval here? And one of them was like 39.5 to 42.3. Well, that doesn't make any sense because our sample mean of 38 wouldn't even be in the interval. Not only does it have to be in the interval, it has to be smack dab in the middle, right? The whole point of confidence interval, you don't get too lost in the equations, too lost in looking at the standard normal distribution. The whole originating idea is that I'm taking my sample mean, it's the best guess that I have of where that true population mean is. So I'm going to build an interval around that sample mean that hopefully, with a certain level of confidence, it will include that true population mean. Any questions on this? Okay, so I'm using some kind of dumb examples, but you can imagine, like, if we're talking about the average weight of a production process, this comes to medication, right? I want to get as narrow a range as possible, right? So I want to get a really large sample size that kind of guarantees that I'm increasing. Sorry, I wrote 2 here. No one called me out on it. It should be an N, or maybe I wrote N and just was squiggled real bad, right? Yeah, once I got everything plugged in, I can get this confidence interval, and now I can start to make some interesting statements, right? So if someone, told me here, pregnancies usually last however many, 40 weeks, I can say, no, based off of my sample evidence, 40 is not the true population mean. The true population mean is somewhere in this range, okay? All right. Moving a little bit quicker. I think we'll do this and I'll kind of come back to it. So let's say I gave you this example instead. Okay. So kind of the setup from the previous problem. Let's say I go over to the rec center and I grab 35 of their 45-pound weight plates, right? So what ends up being true is if you were to weigh them, they don't all weigh 45 pounds. Some of them are like a little bit more, some of them are a little bit less, right? Maybe one of them is 46 pounds, one of them is 44 and a half. So you take 35 of them, you find an average weight of 46.5, where you're like, well, the average that I found from my sample is greater than 45, right? This product isn't what it says it is, right? But, if the true mean was 45, it could be very possible that I saw a sample mean that was a little bit above that. Okay? So I want to build this confidence interval. So I'm going to build this confidence interval for what level of confidence here? Alpha is 0.1. 90% confidence, right? There would be 0.9 in the middle or 90% in the middle. So I want a 90% confidence interval. My alpha is 0.1. I've got my sample mean. I've got my sample size of 35, and then assume that we somehow know that the production process of pouring these plates has a variance of 25. Okay? So I'll give you guys a little bit of time to work on this one, and we'll kind of come together and then talk about it. Listen, feel free to work with the people around you, talk to people around you, try to figure it out. All right, let's fill out the board, so I'll be nice today. So, trying to do the exact same thing as I did in the previous problem, right? I've just got a different kind of setup. Right now, I'm looking at kind of this average weight of 46.5. So, I should be basing my confidence interval around that sample mean value I found. So, which of these confidence intervals doesn't make any sense at all? Yeah, D, why? It doesn't even include the sample mean that I found, right? Not only is it not centered around it, it doesn't even include it. Now, I think if I look at some of these other ones, 46.5 is probably not in the middle of this one, right? Or this 46.5 would be about 2 away from the lower bound, but about 3 away from the upper bound. Right? So that one probably isn't going to make any sense. So from there, I've got it narrowed down. So what I'm gonna do to actually find what those values are, I plug in my sample mean value, but I've also got this variance of, not 9, sorry, that's the previous one. What was the variance? Variance was what? 25. Sample size was 35. Right? Now I could have done this intermediate step ahead of time. So if I just wanted to calculate what that standard deviation of my sample means was, I kind of do the intermediate. I think it's like 0.84-ish, right? Now I've just got one value. So the only thing left I need is what's that z value? Well, here we had an alpha of 0.1. So when I wanted half of alpha in each tail, I actually wanted what? 0.05 in each tail. When I look 0.05 up in the table, what do I find? So we'll go here, 0.05. We're in between these two values. So negative 1.64 and negative 1.65. So now I want to go 1.65 standard deviations above and below to get that confidence interval. Okay. So we had that alpha of 0.1. That was the total area outside my interval. So each tail would have half of that. Half of 0.1 is 0.05. I then looked 0.05 up in my table. It's not up here anymore because I scrolled down. I looked up 0.05. Closest I could get was in between these two values, which corresponded to the number of standard deviations or a z value of negative 1.6. Still going up, negative 1.64, negative 1.65. We use the higher of the two. Any questions over anything in that process there? So if we do that, right, I did the intermediate value of 0.84. I found that standard deviation just to make it a little bit easier on myself. We've got our z value. Now it's just a matter of getting those things plugged in. All right, got everything that we needed. We get an upper and lower bound of 45.11 to 47.8. Right, I add this margin of error to the upper bound. I subtract that margin of error to my lower bound. Right? So I'll go back here. So 45.11 to 47. Maybe I'll go back. There we go. 45.11. Oh my gosh, come on. There we go. 45.11 to 47.89. Right? Hopefully everybody gets this. All right, everybody can answer in. I'm gonna close it out. Now 25 of us, 26 of us. All right. So why is this an interesting example? Based off of my confidence interval, what could I go to the company and say? These are supposed to be 45-pound weight plates. Your production process is not hitting that on average, right? Because the true population mean at the very lowest based off my interval, based off the sample evidence I found, is 45.11, right? So with 90% confidence, I go to this company and say, look, you got to change something about your production process. It's not targeting the weight you say it. And that's really trivial if I'm talking about 45-pound weight plates. It's not trivial if I'm talking about medication or a steel I-beam that's supposed to weigh a certain amount of supportability, right? So, you know, if we could do this with much more important applications, I'm just kind of giving you some of these easy ones to start out thinking about is, but yeah, the real power of confidence intervals is I can look at you and say, based off of that sample evidence I found, based off the sample mean, true population mean is somewhere in this range. And if you don't want, you want the mean to be somewhere outside that range, well, we got to change something, right? Because right now it's somewhere within this range of values. Now, one thing I'll point out in this example, I could tell them that with 90% confidence. What happens if I want to tell them that with 99% confidence? And I see the exact, I took the exact same sample. So my sample mean doesn't change. The original variance on the production process doesn't change. My sample size doesn't change. The only thing that changes if I want to say this with a higher level of confidence is if I want to say something with a higher level of confidence, what's going to happen to alpha? So if I go from 90 to 99%, alpha is going to go from 0.1 to 0.01. So I'm going to have what? 0.01 over 2, or instead of 0.05, I'm going to have 0.005 in the tail. That means that my z value is going to have to be larger, and here we're negative values, so larger in magnitude. I think if I look it up, we did it earlier, get negative 2.58. So my Z value now is higher, right? I want to say things with a higher level of confidence, makes that alpha over 2 value smaller, meaning you have to go a higher number of standard deviations to use a higher Z value. That's going to increase my margin of error. I'm going to end up with a wider confidence interval. Notice, I'm going to end up with a wider confidence interval. What's probably true about the 99% confidence? That lower bound probably goes below 45, and I can't tell the company with 99% confidence that the true mean couldn't be 45. Right? But with 90%, I could. Questions on anything there? So, I think if there's anything else I want to say. We already went through this. I think we'll say this for next class. So you guys got done with you guys a little bit earlier. We'll do the population portion next class. We'll also look at how we do this in Excel, right? So Wednesday's class will be kind of really important for that next Excel assignment. That's going to be basically the rest of it is what we're going to cover on Wednesday. Okay. All right. We'll see you guys on Wednesday.